mention, I maybe skipped a little bit over the definition of this E hat, in case it was unclear, is the empirical estimation of F. So you just imagine a uniform distribution on the training sample and treat it like, so in many respects you can view a lot of these learning results as just estimating the difference between estimating things on the sample-based distribution and the true distribution, and that sort of can be seen as the way. So this is just the average of the evaluations of F on the training set, this empirical thing. So we'll be using that a lot, so I just wanted to make sure people were clear about that. Okay, so this was what we got for the difference in the empirical estimation here, and that gave us this bound on the difference, the change in D of S. And as I said, we can then plug and play. So this is C sub I in the case of the McDiarmid. So if we just plug that in, if you remember the form, I've already written it in this delta 1 minus delta form. If you remember, that's what it looked like in that form. So the sum of the CI squareds comes in here, and we have F minus the expected value of F. So here we would have D of S minus the expected value of D of S plus, and then we just substitute in that value of CI that we've got. There it is. There's the value of CI. And the sum of the CI squareds just gives it an M factor. So we get M times this squared. We can take that inside, make it M squared divided by M, take the M squared inside the square, and we get 4M beta plus 1, and then take the square out of the square root, and we get to that. Hopefully that's okay. So that's looking pretty well like a bound on the generalization, except that we don't know what this value is. And in general, this will be a very much harder thing to compute, though, again, perhaps I should emphasize, a lot of people have spent time estimating the expected values of generalizations, so, this may be something that can be done, and in this case it can because of these assumptions about the beta stability or uniform stability, and we can actually bound that E of ds by 2 beta, and again, I'm not going to go into the details of that. It's a little bit tricky, but essentially you're using the fact that you can substitute, when you remove the example, you can view it as a test example, and so you get the estimation of the true error there. But I don't want to go into the detail. If you're interested, I would recommend the paper by Bousquet and Eliziev. Anyway, putting it all together, this now gives, because remember D of S was just the difference between the true expectation of the loss and the empirical estimation of the loss, and so here we have it now as a complete bound, the true estimation, empirical estimation, the 2 beta from here, and the previous bit we got from before, and this holds with probability at least 1 minus delta, so this is a nice generalization bound. It's interesting, it has a very different form. It's not looking quite like what we're used to, with the complexity term. It still has the nice dependence of log 1 over delta, the benign entry of the confidence, so that you can apply this many times without too much cost. But notice that beta is going to have to be small for this to be a good bound. Beta is going to have to be much less than 1, and indeed less than 1 over m, because this 4m beta here is going to kill us, and S beta is of the order of less than 1 over m, because remember this is a probability bound here, so we don't want to have anything too big there. So in the case of 1 norm SVMs, we can there is a bound of this type, which is an interesting fact. C is here the constant in the that controls the size of the sum of the psi squareds. You remember we had the objective function is the norm W squared plus C times the sum of the slack variables. That's that C. So clearly this is not going to work when c goes to infinity. In fact, c is going to have to be quite small, less than r squared to get anything, 1 over r squared to be anything useful. So it works, but sort of just. So I wouldn't, sort of recommend it, if you like, as a sort of way of bounding generalization, perhaps for support vector machines, but it certainly can be applied in many other applications as well, and it's a very interesting technique. So at that point, I think I'll close the story of stability theory in this approach. As I say, my main aim here was to give you a flavor of applying these bounds, and I think now is the moment to bite the bullet and go for Radamaca. Okay, so this is a new way of measuring the complexity of a function class. It's sort of like a replacement for the VC dimension or the fat shattering dimension that you are using now as a in the back of your mind as a good way to talk about complexity. So Radamaca is now the sort of the name of the moment. Now I want to sort of lead to why we use Radamaca complexity by showing how it arises in a rerun of the proof using the double sample trick and symmetrization, but using this expectation notation. And you'll see that it sort of comes out very naturally. And then we'll look at its properties and see how we can use it in the case of support vector machines and boosting and so on. So that's the strategy. So let me try and take you through this, and you'll see that we'll have many recurring themes from yesterday coming in here. So the first thing, and I mentioned this before, we can easily write down this expression by observing simply that this and this are the difference between the true estimation of f and the empirical estimation of f for some f in our function class, and that's certainly going to be less than or equal to the sup over all possible f's, or h's in this case, in the function class. So this is a very trivial estimation, and this was the point I was making, that in this case, in Radamaca case, we don't consider the particular function given by our learning algorithm. We make the inferences for all functions in the function class. So this is, if you like, our bounding this is why we often refer to uniform convergence, in the sense that it's uniform over all the h's in the function class. We're trying to make sure that for no h can we get a very significant deviation between the empirical estimate of its error and the true estimate of its error. So I'm now going to just abstract away and make these functions just general functions mapping from some set z to a bounded range 0, 1. And we're going to just plug through and see how far we get. Initially we're going to apply McDiarmid's to bounding this, right? So we're going to try and bound this. Okay, and we're going to start by looking at McDiarmid's inequality and seeing how this can change from its expectation over the sample. Okay, so this is, of course, the sample affects this through its effect on this guy here, right? The expectation here. It doesn't affect this part, okay, because this is the empirical estimate. So applying McDiarmid involves estimating how much this can change. So this is our function f that we're looking at in the McDiarmid theorem, how much this can change if we substitute one example for another, okay? But we're thinking of a fixed h. H doesn't sort of depend on s, okay? So we're fixing, I mean it's the sup of h here. H will depend, because it's the empirical here, so the amount that it can change is bounded by the amount that this function can change on a single example. Because if we're looking at this soup, we could certainly use as our soup the particular h, and if that doesn't change by much, then obviously the soup can't change by much. I mean, if no function can change by much, the soup can't change by much. And by substituting a single example, we can only actually change that by 1 over m, because it's the range of the functions is the range from 0 to 1, and we're taking an empirical average. Clearly, we can't change by more than 1 over m. So we just plug into our usual bound here, where Ci is now 1 over m squared. And because, if you remember, the form of this has some Ci squared on the top, that's some Ci squared, some 1 over m squared, but there are m of them, so 1m cancels, so you get 1 over m. So this is log 1 over delta 2m. And this is the empirical, and this is its expectation. Okay? So that's okay. Okay, now, this is where we go to the ghost sample Radamaca style. Okay? So now what we're going to try and look at is this term here. So we keep dropping terms. We say, okay, we start with this, and we say, oh, forget about this, let's bound this. So we bound this, and we get this. And now we say, forget about all this, let's bound this. Okay? So we're going to focus in on that. And what we're going to try and do is do the double sample trick. What we've got here is this E of h, that's the true error, and we're going to replace that with its expectation over a ghost sample. And of course its expectation of a ghost sample is the true error, because it's a particular fixed function. Okay, so here's that. The expectation over S of the empirical error is actually the true error. Okay, so here, if we replace that E of h here by this quantity, we get the soup of the empirical estimation on the ghost sample, which I'm denoting by S tilde. And now I've written out explicitly what these empirical averages are. And this is an expectation over S, the actual sample, and this is given S. We're doing this calculation. Is that notation okay there? Is that? Do ask if there's anything that's not clear. Okay, so it's just the trick of replacing the true error by estimating it on a sample. Okay. Now, the next thing is that we can remove that expectation here through the soup. And we will only actually increase the value. So the reason for that is, okay, we're going to gradually try and get these expectations together on the outside here. So the reason we can move it through the soup is that if we have the expectation inside the soup, we don't have the option of optimizing h with respect to a particular S tilde. It's sort of h has to be optimized to the average of the S tildes. But if we move the S tilde outside, h has the option of not only optimizing with respect to S, but also with respect to S tilde. So it can do better. It can actually get bigger. And therefore, the actual expectation will increase, or can increase. So we actually get that this now, that was what we started with, is less than or equal to the expectation of E with respect to the sample and the expectation with respect to the ghost sample of this soup, which was what was left inside, which was this sum where we had the average of the ghost sample and the average of the true sample. And now I've just put the two sums together to make them into a single sum. Okay. So now we're at the point where we can do symmetrization. So things sort of go very smoothly in this view of the world. You sort of slot these things in as you go. Symmetrization will now correspond to just, again, we're going to do the same thing, exchanging corresponding elements. You remember we took the first element of the sample and the first element of the ghost sample and swapped them, or didn't, and the first element, second element with the second element. So now if we do that, that corresponds to just swapping these two guys, right? Z1 tilde and Z1 here, and Z2 tilde and Z2. Well, what happens if we did swap those two? All that would happen would be that the sign of this sum, this entry in this sum would change. Okay, instead of being HZI Z1 tilde minus HZ1, it would be HZ1 minus HZ1 tilde if we made the swap. So we can make the swap by just multiplying by a minus 1. So that's the next trick. Sorry, I've gone the wrong way, haven't I? Oh, yeah, no, that's right. So that's the next trick, is to just put in a sigma I here, which is going to be a variable which can be plus or minus 1 with equal probability, and add that sigma into the expectation here. So that now is an expectation over the sigma, and because of the fact that the two samples are generated according to the same distribution, there's nothing special about, you know, S and S tilde, they're equivalent. Swapping will not change the value of the probability of the expectation. So exactly the same argument we had before when we were saying, okay, if you choose a sample then apply a random permutation, it won't change the probability of that particular set of examples being generated. If we swap those two, it won't change the probability. It's just as likely under that choice of sigma as under any other choice of sigma. So adding in those will not change the probability. Okay, so you know, things go very smoothly, and now at this point what we're going to do is to split apart this sum now into the two sums, sum sigma I h zi tilde and some sigma minus some sigma zi, sigma I h of zi, and then that's the difference of two things, and we're going to bound that by the sum of the absolute values of the two individual sums, but they're both the same sum effectively. They're both sum sigma I h of zi expectation with respect to some sample, and we're going to also take the soup into both of them, which again is just going to increase the value because we can take the soup on either, and so we just get twice this value here. So there's quite a few steps in that stage from here to here. Maybe it's a little condensed, but hopefully you can see that basically this sum here and will be, if you separate it out, will have exactly the same sum. This sum will occur twice, once with z tilde and once with zi, and effectively we can take the soup to be soup of both and separate them into two, and will only increase the resulting value. And so that just, then the two just comes outside and we get this expectation here. Is that okay? Or I can write out some steps on the slide if you prefer me to. There's people looking a bit blank. Maybe I should try and do a bit more here. Sorry, I maybe didn't. Let me just write this out first. Okay, so I'm just going to do. Okay. So what I've got there is the starting point. Just if you look at the this bit here, right? Okay, I'm starting with just this part here. Okay, and I'm going to work with that. So let me cover this up. So there's that quantity. So the first thing we do is that's the soup of 1 over m sum sigma I h of zi tilde plus 1 over m, minus 1 over m sum sigma I h zi. Okay. And now what I'm going to say is that that's less than or equal to the sup of 1 over m sum sigma I h of zi tilde plus 1 over m sum sigma I h of zi. And then I'm going to say that's less than or equal to, I can choose the sup for individually. This is sup h in h. So this is one size, but if I can choose the h for this part and for this part separately, I'm going to do better still. So this is less than or equal to sup h in h 1 over m sum sigma I h of zi tilde plus sup 1 over m sum sigma I h zi h in h. And that's just equal to twice sup h in h. Sorry, the expectation of that. Sorry, I can't make this step here, but since these are the same, generated by the same process, the sup of the expectation of this and the expectation of this are identical. And so you just get twice that expectation. Is that okay? Yeah? Okay. I'll run through the steps again at the end just to sort of put it all together maybe, but give you a flavor. So that then, that then separates this out into one sup and this into the other sup, and because you've got the expectations, they essentially become independent and you just get twice the expectation over one of them because they're identical. Okay, so that looks quite good. We seem to have got quite far. And then, you think, well, I've done enough for today, so I just say, that's Radamaca complexity, and I'm finished. Okay, so, okay, fair enough. And so that's the definition of Radamaca complexity. That is it. Okay, so it doesn't seem a particularly sensible thing to do at this point. It just seems like you run out of steam and you don't know what to do next, so you just make a definition. Okay. But it amazingly seems a very sensible thing to do in the end. And we'll see, that this is actually it. But okay, so if we just make that definition, that is the Radamaca complexity, there it is. That's just the definition of the Radamaca complexity. I'll come back to talk about what it means and so on. And we get this, right? So let's just go back and see the stages we went through. So if you remember, we started by doing this. So we had E of f of z was the empirical, and then we had this sup thing. And we said the sup thing was less than or equal to something plus this bit. So we're going to have to keep this bit. But okay, we're just going to really replace this by this and add in a bit. So what was this? This was the thing that we essentially got down to the Radamaca complexity in the end, by definition. And so we end up with simply E of f of z, the expected value of this function, is the empirical value plus the Radamaca complexity plus this extra term that we had right at the beginning. Okay, so that's basically it. Maybe now let's just look at this Radamaca complexity term. Maybe just go once more through the steps. I mean, the critical step was, the first step was quite easy. That was just a Radamaca to get to the expected value. Once we got to the expected value, we could apply this nice little substitution of a sample to estimate E of h within the sup. That gave us this expectation over this guy in place of this guy, and that's just an equality, because if you just work out this average and randomize over the choice of the samples, you're going to end up with a true estimation. Then we were able to bring this E of s outside and only increase. And then we were able to, that gave us that one. Then we were able to introduce the symmetrization by this sigma I plus minus 1 swapping of those two in a very simple way. It became a very simple trick. That was this bit here. And then we made those steps that I made a bit more explicit to get to this thing, and then we said we've done enough, and that's Radamaca complexity, and that's it. Okay, so that's basically it. Now let's look at it and see what it makes. Does it make sense? Well, it actually has some very nice sort of flavor to it. Why is it called Radamaca complexity first? That's because Radamaca variables are these +1, -1 random variables with equal probability. So that is actually a Radamaca sequence, and you can think of this as, if you like, a random classification that you're being given, or a random vector of noise, +/-1 values. And what we're asking the function class to do, we're trying to find a function which aligns very well, has a high inner product with noise. Okay, so if you imagine this is just the inner product between this -1 +1 random vector and the value of this function f on the training sample. So you've got the random noise over the training sample, think of it as random labels, and you're just trying to align your function, find a function that aligns as best it can with that random noise. And then you're saying, what is the expectation of that over the choice of that random noise? And then furthermore over the choice of the sample. Now that actually is a pretty good measure of complexity if you think about it. You know, a function class that can align well with random noise is obviously pretty flexible. And one that can't is good. You know, I mean, if you've got a sensible function class, it shouldn't be able to align with random noise, and so the Radamaca complexity should be small. And that's sort of almost like if and only if. You wouldn't expect a function class that could align with noise to do well in learning. So it turns out, yeah, okay, maybe this isn't such a bad idea. The other point about, you know, Radamaca complexity as compared to, say, VC dimension as a function is that it's distribution dependent in the sense that it involves an expectation over the choice of the sample. So if you look at this expectation here, there's a further expectation over the choice of the sample. So you're saying, okay, for any given set of training points, I can estimate what the thing is. But I'm allowed to take the expectation over that as my estimation. Now, with a VC dimension, if you remember, we had the soup. You know, we just said, is there some set of points which would have this high shattering, or, you know, we could do this very high number of different functions. Now, let's say you had a function class where that did exist, but the actual input distribution was not focused on that at all. So that in your actual inputs that were being generated were in this region that was much more benign and not so difficult. VC dimension will be killed because you have to take this worst case sort of estimate. But the Radamaca complexity will effectively pick up on that fact that the place where the data is far more benign. And you may say, well, how do you estimate that? Well, we'll come to that in a minute. Now, in fact, if we've got time, he said. Right. Yeah, I think we've just got time for this, and then we'll finish. Well, we can actually get rid of that expectation over S as well by taking what I'm calling the empirical Radamaca complexity. The empirical Radamaca complexity is simply the complexity estimated on a particular sample. So assume, you've got a training set. You could estimate the Radamaca complexity on that training set by simply, doing this expectation of the soup over just the random noise on that particular training set. Right? And you might say, well, that's not the Radamaca complexity, so how are you going to use it? But we can do our usual trick of applying yet again McDiarmid concentration inequality, and the Radamaca complexity is also concentrated. So you can show that, the Radamaca complexity, if you substitute Zi with a different Zi hat, is not going to change by very much. And so its empirical value is close to its expected value. Its expected value is the Radamaca complexity, so you can bound the empirical Radamaca complexity by a very small deviation from the true Radamaca complexity. And so you can get a result of this type with probability 1 minus delta. You've got the true error less than the empirical error plus the empirical Radamaca complexity estimated on the sample, plus a little bit more here because you've got 2 bits of McDiarmid, so you get a 3 log 2 over delta over 2m. So now you're actually able to estimate the Radamaca complexity on the sample. So not only have you got away with actually not taking the worst case, in the sense that you have to worry about the distribution of examples. Maybe the bad part of the function class is in an area where there isn't much probability mass. Not only do you not have to worry about that, actually you just look at what the Radamaca complexity is on the sample you have and just deal with that, which is a very nice property, I think. Yeah?
On the last slide. The D.
Oh, D, sorry, yeah, that was old notation slipping in. That was just, that should be P or just not there. Sorry, yeah. It's just the underlying distribution generating the data. Sorry, this, I must have copied from some... Ignore that D. This is just the true probability, yeah. Sorry, yeah. Any other queries? Okay, so let's break for coffee, and I'll be finishing in the afternoon today, actually. I think Chris Bishop will be starting after the break.